Okay guys, in this video I'm going to do a couple of proofs of vector identities. The reason for that is the second one is important for what we're about to study later. We're about to talk about the unit tangent vector, the unit normal vector, and then later the binormal vector. And this is an important property that we'll be using when we talk about that, but I don't want to just force you to assume it. I'd like to prove this to you. And this is based, and the proof of this one is based on the proof of this one. So I'll just do the top one first. It looks like a product rule, doesn't it? You've got the derivative of a product. Here's your first function and your second function. But it's not a regular product, it's a dot product. And it turns out a dot product works just like a regular product. The derivative of this vector function dotted with this vector function is the first dotted with the derivative of the second plus the second dotted with the derivative of the first. Now I know that normally when I say the product rule, I say it in a slightly different order, but the principle holds. And remember, dot product is commutative, so r dotted with u prime is the same as u prime dotted with r. We're going to multiply components and add, so we can multiply in any order we want. So u dot v is the same as v dot u. So with that in mind, yeah, this is just an extension of the product rule. And you might say, how on earth? How does that even happen? So we're going to prove this first one, and then we're going to use this result to prove the second one. So let's prove number one. It's actually pretty simple. Let's assume that r and u are vectors in n-dimensional space. So r is going to have components. Let's call them x sub r1 of t, x sub r2 of t, all the way through x sub rn of t. And I'm putting that r on there just to say that they're components of the vector r. And there are n of them. So r takes a number t and it maps it to a point in n-dimensional space, mapping it to x sub 1 through x sub n using this function. And similarly, u is going to do the same thing. So I'm going to call this x sub u1 of t, x sub u2 of t, all the way through x sub un of t. So u takes a number t and it maps it to a point in n-dimensional space as well. If I take the dot product of these two, I'm just going to end up multiplying component by component, right? That's how the dot product works. So I have x sub r sub 1, that's a function of t, times x sub u sub 1, also a function of t, and then we're going to add this times this, and then we'll add the next one times the next one, and then we'll add, and we'll keep going. We're going to have n terms. The last one is x sub r sub n of t multiplied by x sub u sub n of t. Now these are scalar functions. In each of these component functions, we input a real number t and the output is a real number. So this is just a real number times a real number for a particular value of t. So yeah, I've just got n terms and I'm multiplying real valued functions of t and I get this. I'm going to use this alternate notation. It's just shorthand. Remember from the end of Calculus 1 or maybe when we're doing all those Riemann sums in Calculus 2. What I'm doing here is I'm taking the ith component, x sub r sub I of t, and I'm multiplying it by x sub u sub I of t. So I multiply the first components together, then I multiply the second components together, and then the third, and then eventually the nth, and we get this. And we're going to do this, we're multiplying these as I goes from 1, that's my first term, through n. So this is just the sum of a product of two functions of t. Okay. And this says, okay, once you do that, you've got this take the derivative of that and prove to me that that's exactly the same thing as this over here on the right-hand side. So we're assuming this. So we've got two vectors. Their components, they map to points in n-dimensional space. When we take their dot product, we get this. This is a scalar. It's a scalar function of t that came from multiplying all those components and then adding them together. Now we want to take the derivative of this. Well, the derivative of this is just the derivative of this. I'm going to stop writing of t here just to make it a little cleaner. But remember, this x sub r sub I and x sub u sub I, those are functions of t. So I've got the derivative with respect to t of this sum of terms. And we know the derivative of a sum is the sum of the derivatives, so we can bring that inside. Now you might say, Miss Townsend, I don't know what you're talking about. That's okay. Just imagine looking back here. I'm taking the derivative with respect to t of this sum. So I'm going to take the derivative of the first term, and then I'm going to take the derivative of the second term, and the third term, and the fourth term, and then eventually the nth term. That's the same as doing this, bringing that derivative operator inside the summation. So I'm saying the derivative of this sum, which is this, is the sum of the derivatives. So I just go to each piece, and I take the derivative of each piece. I hope you're with me. Okay, so I've got x sub r sub I, or x sub ri. That's one component function, and it's being multiplied by, these are scalar functions of t, x sub u sub I of t. Well, if I've got a function of t times a function of t, and I'm applying the product rule, well, if this is my first function and that's my second function, according to the product rule, oops, that's I equals 1 through n. The derivative of this product is the derivative of the first times the second plus derivative of the second times the first. And we're adding all of these up. Now I can take that summation operator and I can apply it to both of these pieces. This says plug in I equals 1, add those together. And then plug in I equals 2 and add that. And then plug in I equals 3 and add that. Isn't that the same as substituting I equals 1 here and doing that for I equals 1 through n? And then substituting I equals 1 here and doing that for I equals 1 through n? I hope you're saying, yes, Miss Townsend, that's absolutely right. If not, you should check it out. And you might want to do this for like n equals 2 or n equals 3. It might look a little bit simpler. So we've got this over here and this over here. Oops, that's a derivative there. X sub r sub I. Multiplying both of those and you're taking the sum. Okay. Now I claim that this is a dot product of a derivative with one of our vectors. Let's check it out. If I substitute in x equals 1, I get x sub r sub 1 prime times x sub u sub 1. And then I substitute in I equals 2, I get x sub r sub 2 prime times x sub u sub 2. And then I'm going to keep going until I get n. X sub r sub n prime times x sub u sub n. All of this is just that one right there. And then we're going to add what we get for this one over here. When I substitute in I, so there's my double star, and that's my star. So when I substitute in I equals 1 here, we've got that prime times x sub r sub 1, x sub, when I equals 2, I get x sub u sub 2 prime, x sub r sub 2, and we keep going. Eventually we get x sub u sub n prime and x sub r sub n. That's a dot product. Look at these terms. That's x sub r sub 1 prime, and x sub r sub 2 prime, and x sub r sub 3 prime is going to be over here, and eventually x sub r sub n prime. So when I take that out, and I think of that as a vector being dotted with another vector, that first vector is, well, because of these r's here, remember? Those r's told us we're looking at components of r, but we're taking their derivatives. So this is r prime, evaluated at t. And then these guys, those are the components of u. I got u1, u2, un. So I'm taking r prime and I'm dotting it with u of t. Over here it's similar. I've got u1 prime, and a u2 and a prime, and a u sub n prime. So this is u prime of t. And if I look at these guys, there's an r1, an r2, and an rn all the way across. So we got rt there. And we're adding those together, so we're adding these together. And I think that's what our identity said. The order might be different, but that's okay. We've got r prime dotted with u, and u prime dotted with r, and the dot product is commutative, so we can change the order if we want, and then we're adding them together. R prime dotted with u, and u prime dotted with r, and they're added. So we've proven that first result. Okay, so this checks out. We've got a product rule for the dot product of two functions. So it's a dot product, and it works just like a product rule. Now, I'm going to use this fact, or I'm going to use this fact to prove this one. It's actually pretty simple. So I'm proving the second one, and it said, here's what I'm trying to prove. I'm trying to prove that if r dotted with itself is a constant, then if I take r and I dot it with r prime of t, I'm going to get 0. It's actually pretty simple. Well, we know from before, well, let's just make our assumption. We always want to assume the if part of this statement. So assume that r dotted with r is a constant. Then if I take the derivative of r dotted with r, then I'm just taking the derivative of a constant. And we know the derivative of a constant is 0. Say, okay, so what? Well, according to that last thing that we proved, the derivative of r dotted with r is derivative of the first function dotted with the second, plus the derivative of the second function, which also happens to be r, times the first. But it's a dot product, and dot products are commutative, so you can change the order if you prefer to. I'm going to put r first. So I've got 2 of those. And this has to be 0. Well, the only way the dot product of 2 vectors is 0, well, yeah. So I've got the dot product of 2 vectors is 0, and I multiply by 2. So the only way that's 0 is if that dot product is 0. And that's what we were trying to prove. You might say, oh, what does that mean? What's the significance of that? Well, what that's telling us is, if I take r and dot it with itself and I get a constant, then r and r's derivative are perpendicular to each other. Think about that for a second. R and its derivative are perpendicular. So here's r of t. And if I take the derivative at t, I said perpendicular, but I meant orthogonal. They meet at right angles. So as r changes by a little bit, the change the derivative is going to be perpendicular to that. The instantaneous change in r with respect to time is going to meet this at a right angle. Okay. Now one other thing that we can talk about here is what this means. Remember r dotted with r, that's, if I take a vector and I dot it with itself, I get the length of that vector squared. And we've proven that before. So what we're saying is if the length of the vector is a constant, then if I dot r with its derivative, I'll always get 0. So let me put that in words. We've proven this thing, which just doesn't seem very important, but it's actually pretty important. It's insightful. If the magnitude of r is a constant, so that it's not changing, then r and its derivative are orthogonal to each other. So if I'm changing the length, or if I don't change the length of this, then when r changes, it's going to change in this direction. I'm not sure if I agree with that. Well, think more about that, and we'll discuss that a little bit more when we talk about unit tangent, unit normal, and the binormal vector.